Okay, I think, yeah, the recording has started. So, hello everyone, and welcome to the final talk of this semester. So today we have Nikita from IISc, who is a fourth year PhD student working with Professor Binod Ganpati, and she will be talking about control flow attestation. Over to you, Nikita.
Thank you, sir. Hello, everyone. Today I'm talking about control flow attestation, which I have been working on since almost 2 years now. And I'm part of Computer System Security Lab here. And so in this talk, I will be describing what control flow attestation is, followed by the different prior works which exist in this domain, including our own work. And then towards the end of this talk, I will be discussing what gaps exist in this area where we can do further research and try to solve those problems. So let's get started. And Yes. So, what is control flow attestation? So, before I describe that, the word attestation simply means to verify something as true or authentic. So, attestation has the work in attestation domain dates back to early 2000s when it was started, and it was used for attesting the boot sequence of the system to ensure that the system has started correctly. So, it is using the softwares which are not malicious and they have been started correctly. So now, as the work in attestation progressed, so it was used to attest different properties of the system, like to attest the memory in order to detect if there is any virus in the system or not, it whether is there is a rootkit or it has been tampered with or not. Now, control flow attestation is also a type of attestation which is more rich because it is not a static attestation, but it is a runtime attestation. So it attests not just the that the program binary is loaded correctly, but it also attests that the program when it is running, so whether the program is running correctly or not. So in any attestation protocol, there are these two parties. One is the prover, other is the verifier. Here, I'm using name Peter and Victor to refer to the prover and the verifier. So consider that there is a patient named Peter, and Peter is using, say, a medical device, such as a syringe pump or insulin pump. And Victor, who is Peter's doctor, wants to be able to send remote commands to this device. Okay, for example, inject 1 ml of medicine. Now, what does Victor want? Victor wants to ensure that if he is giving a command to the insulin pump, then whether that command has run correctly or not. Now, this will serve as a proof that the operation was performed. And so, if later anything happens, then it can also help detect that what went wrong or whether everything was happened correctly in the past or not. It acts as an audit trail. Now, to do this, to control flow attestation, what we have here on the right hand side is a control flow graph. Okay, so when you give this command, so in response to this, some program will be executed, and I'm representing here that program as this control flow graph. And when you give this input command to this program, so let's say that this highlighted yellow path is executed in this program, which is the sequence of these basic blocks BB1, BB2, BB5, and BB6. And what we want in attestation is to be able to record exactly what path was executed by the program. Okay, so to do so, we can leverage some secure hardware which is present on this embedded device. And so the secure hardware is going to record the execution of this program when it is executing, and it will record this sequence of basic blocks, and later it will sign this sequence of basic blocks and it will send it back to Victor. So this execution of this executed control flow path, which is the sequence of basic blocks, is sent back, and it serves as a proof of execution which can be verified by Victor against a measurement database created ahead of time, which maps the various input commands to the paths in the program which are considered valid for that particular command, and then it will be able to check whether the command which was given to the remote device it ran correctly or not. So control flow attestation basically contains these two parties, prover and the verifier, and the assumption is that they are not co-located, they're remotely located. And so when you give a command to this prover device, you cannot observe what the device is doing because it is remotely located. So you want to generate a proof of execution. And to do so, we are here leveraging some hardware, say secure hardware, and we are recording the uh, path that the program is taking at runtime and sending it back as as a proof of execution to the verifier to be verified against some measurement database created ahead of time. And we assume that this measurement database is created in a benign setting, and so that it is so if it is mapping a command to a path, then we assume that that is a valid path to be executed for that particular command. Now, you may say that, okay, this is the program and I'm giving this command, then the correct path should be executed. So what can go wrong? So there are a number of things that can go wrong. First, of course, is that there can be some benign faults. So the some configuration was not set properly, so the program ran incorrectly. But apart from that, there could be some malicious attacks also on the program. So there are a number of possible threats. The first one can be that the attacker can modify the binary which was loaded to execute. So this we can detect with static attestation, right? And the second one is code injection. So the program can have some memory vulnerabilities such as buffer overflow, which can be exploited to inject some new code into the program. And then the attacker can try to execute this code. Then the third type of possible threat is code reuse or return oriented attacks, in which the attacker changes the jump addresses like return address or the code pointers, and therefore it tries to execute some code sequences in the program, and which are called gadgets, and thereby it stitched together these code sequences in the program to execute some arbitrary operation which was not originally part of the program. And this line of work, which is this type of attacks are called code reuse attacks, and these are well known type of attacks, and it has been shown that these type of attacks are possible on different kinds of hardware and softwares. And the fourth type of attack is input or data corruption. So the attacker can change the input that you are giving to the command, so that you're giving to the program. So instead of giving this input command inject 1 ml medicine, it can just change the amount of the medicine, or it can change some other data for which your program is reading. Now, lastly, the physical attacks, we consider them to be out of the scope for this work. So if the attacker has physical access to the device and makes any physical changes or tampers with the device itself, then we cannot detect those kind of attacks with this particular approach. So now to give example of these runtime attacks, we consider the CFG, where the nodes are the basic blocks and the edges are the control flow transitions, such as the branch instructions, call, and return instructions. So here the black lines indicate the expected program flow, and the basic blocks are also highlighted with yellow color to indicate that they are executed in response to the input command inject 1 ml medicine. So if the program has a memory vulnerability such as buffer overflow, the attacker can use it to inject malicious code in the program, which corresponds to this attack threat number 2. And then it can corrupt the return addresses or the code pointers, and it can execute this injected malicious code. Another way is that the attacker can corrupt these return address or code pointers and to execute some other code sequences in the program, like this basic block 4, and which corresponds to the threat number 3. The attacker can also corrupt the control flow can change the branch direction and thereby changing the control flow of the program. Here, the attacker has not added any new edges in the program CFG, but without adding any new edges, it is also able to change the control flow path of the program at runtime. So these are different kind of attacks which are possible and which we want to be able to detect with control flow attestation. So with control flow attestation, what we do is that we record the path of the program when it is executing in an audit log. We call this the CFA log, where CFA stands for control flow attestation. And it here in this example, it is nothing but the sequence of these basic block IDs, BB1, BB2, BB5, BB6, followed by A if A is executed as part of this malicious execution. And when this CFA log is verified by the verifier, then the verifier will be able to detect that a new code sequence was executed, which is not part of the valid code sequence. So in control flow attestation work here, the problem that we are trying to solve is to record the program execution path securely, which has these two parts. First is that the CFA log where we are recording these path that needs to be tamper proof. So the attacker should not be able to modify the values which are stored in the CFA log. It has to be tamper proof. Second, we want to be able to record exactly what the program is doing. So if it is executing, say, this block A, then that needs to be recorded in the CFA log. So this is the problem setting and the attacks that we are trying to solve. We are trying to detect with CFA mechanism. And with this, I move to the what are the prior works in CFA. So here I have mentioned only some of the prior works. So first work in the CFA domain was C flat, which was published in 2016, and C flat stands for control flow attestation only. Another work is OAT, which was published in SNP 2020, and our work Blast published in CCS 2023. Now, what I want you to focus first on the right-hand side column, which is the runtime overhead. So here, as you can see that C flat compared to the baseline incurred approximately 1000x overhead, which was improved by OAT, and it was approximately 500x overhead compared to the baseline, which in our work Blast we have brought down to approximately 1.7x or 70% overhead. So if a program originally runs in 1 second, now with our approach runs only in 1.7 second. And so other aspects which differ the different prior works are, first one is that what part of the program is attested by the approach. So C flat and OAT attested only some critical sections of the programs and not the entire execution. In compare, Blast attests the entire execution of the program, that is from the first instruction to the last instruction in the program. And another factor which differentiate these works and also contributes to the runtime overhead is the path measurement instrumentation locations. So C flat places the instrumentation, basically the instructions which are recording these path measurements. These are called instrumentation locations. So these instrumentation locations are placed in every basic block in case of C flat, while it was improved by OAT and they were placed only in conditional branches, indirect calls, and return or exits. Uh, and therefore, it was able to bring down the runtime overhead to almost 500x. And in comparison, Blast used more optimal approach, and we are able to further reduce the runtime overhead to 70%. And it is not only due to the instrumentation locations, but also we have one more important aspect that I will be coming to later in the slides. Uh, so now moving on. So there are the key assumptions that we have made in our work are, first, the presence of a secure hardware. So we rely on a secure hardware to protect the CFA log, and it is same for the prior works. And in our work particularly, we are using the ARM trust zone. although we are not bound to it. So if there is some other TEE, we can also leverage that to protect the CFA log. But in case of ARM trust zone, it divides the execution mode. It provides two execution modes basically. One is called the normal world, other is called the secure world. So, and it provides the guarantee that any software which is running, even the most privileged software running in the normal world, cannot access the memory or the software belonging to the secure world. And then there is another very important piece of software, which is the secure monitor, which facilitates the transition from the normal world to the secure world by modifying the non-secure bit, which indicates the mode in which the processor is running. Then the second assumption is the presence of data execution prevention, which is nowadays present on almost all hardware. It is a hardware feature which provides the guarantee that the pages which are writable, they are not executable, and the pages which are executable are not writable. So our code pages, we will mark them as execute only, and the data pages are read write and they are not executable, which prevents the attacker uh, from launching any code injection type of attacks. Then lastly, we assume that the application is running on a bare metal hardware, so there is no privileged software running below the application, such as an operating system. And any necessary interrupt handlers are compiled along with the application itself. And so these are the three key assumptions which we make in our work, which are same as the prior works. Now, coming to the threat model of our work, so we assume that the secure world and the secure monitor are trusted, and anything in the normal world is not trusted. And in the normal world, the normal application that we are attesting is
Nikita,
running. Yes, sir.
yeah, my name is Devashish. Can you go back to the previous slide? I just have one clarification question. So
Yeah.
here you assume that there is no OS running in the bare
Yes.
metal scenario.
Yes.
So how the app will basically run if I have to basically execute a program to divide two numbers? If there is no operating system, I am not able to basically understand this assumption. So how the machine will basically interpret the human written code and all?
So it's we assume that any low level code is compiled with the binary. So if there is any it is written for bare metal, and it is compiled with the interrupt handler or any low level code which is necessary.
Oh, okay, okay. Thank you. Carry on.
Nikita, it would be actually helpful if you give examples of why this is actually true. Maybe say firmware or some say power installation where you are actually running this embedded programs. Is that right, or is there other
Yeah,
uh,
yeah,
places
yeah.
where
So
this is? Yeah, go ahead.
yeah, so yes, yes, thank you. Yeah, so this work is actually we are doing in basically in the domain of embedded devices. So this is more true for embedded devices and not the desktop applications.
Ah, that's helpful. Thank you.
Thank
Okay,
you.
and remember, like some of these embedded places are very critical. Like I was hinting towards the power installation, power grid, and so on. There might be some embedded software running which is controlling, whatnot, grid and so on. There, if something malicious happens, it can be disastrous, right? Like so, there, uh, making sure nothing bad is running is very important. And in this context, is the context for Nikita's work. Is that
Yeah, yeah.
right? Like
Yes, sir. Yeah.
Nikita, you can correct me if I'm wrong.
Yeah, no, no, that is absolutely correct. And thank you for the
Thank
explanation.
Yeah, this makes sense also. Now I understand that because otherwise in the beginning I thought that this is a very unusual assumption that why there will be no OS. But now I understand the precise target that you have where these applications would be running. Thank you.
Yes, and I would just like to add that in my current work, which I'm doing currently, I am actually removing the assumption and bringing the OS, and thereby and also ensuring that the CFA mechanism is secure even in the presence of OS. So here, the assumption is actually only because if the OS is present, then it can temper the CFA mechanism that we have here currently. It is not secure in the presence of an OS. But in my current work, I'm working on that direction that even if the OS is present, it is untrusted, we can still have a secure CFA mechanism.
Thank you.
Okay. Okay, now moving on. So here the threat model is that the application is running in the normal world. It is running within the privileged mode, and so it can access the hardware like devices, and it can actually communicate with the secure monitor, which is also which also makes it necessary that the application is actually running in the privileged mode itself. Now, given that the problem setting and the assumptions, now how can we solve this problem? So let us consider this strawman approach to solve this control flow attestation problem, which is to record the program path in a tamper-proof manner. Okay, so consider this CFG here, which is running in the rich execution environment or the normal world, as I just said on the last slide. And we are going to record the measurements in a trusted secure storage in the TEE. Now, whenever a basic block is executed, and then here BB1 is executed, and if the false direction is taken, and then next block to be executed is BB2, then we are going to add some instruction here on this edge, which are going to switch to the TEE and record the hash of the basic block 1 in the TE secure storage, or it can be just the ID of the basic block 1, and it is going to indicate in the secure storage here that the basic block 1 was executed. Now, next, when the basic block 2 is executed and it takes the false branch here, then here again we will have one instrumentation which is going to switch to the TEE and record that BB2 was executed. Similarly, when BB5 executes, we are going to record BB5, and BB6 executes, we record BB6. Now, this approach was this was proposed in C flat paper. Okay, and if I map it back to the example that I gave on the first slide, then this code might be running on Peter's device, and then when this trace has been recorded in the secure storage, say the ARM trust zone, the ARM trust zone then is going to take this trace, which is the path commitment. It is going to generate a digital signature of it, and then it will send it over the network, or it will store it in some memory or some storage from where the verifier can read it, and then the verifier is going to take it and it is going to match it against the path database that was created ahead of time, and then it is going to check whether the program executed correctly or not, or whether there is a violation. Now so in interest of time, I'm actually not explaining the entire details of OAT approach. And here, now moving on to the evaluation of these prior approaches on mbench IoT benchmarks. Here, this column represents C flat work, and the second column is for OAT. So we evaluated these two approaches on mbench IoT benchmark, which is a popular suite of embedded benchmarks. And in particular, we calculated the TEE domain switches encountered at runtime when we execute these programs with these two approaches. So if you'll observe here that for this first benchmark here, C flat incurs approximately 857 million domain switches, which was brought down to approximately 400 million switches by OAT. So there is an improvement. So if I pick some particular benchmark here, which is Nettle SHA-256 benchmark, which computes the SHA-256 hash and take it, then if you so the baseline execution time of this program SHA-256 was only 12 seconds when it is run on Raspberry Pi in our experiments. But if and the 1T domain switch takes roughly 190 microseconds on our Raspberry Pi setup, which is also similar to what has been reported in the prior works. And so if we calculate the time when the program is run with C flat by multiplying the domain switches with 190 microsecond overhead per domain switch, we'll find that with C flat, the same program which ran in 12 seconds now runs in over 11 hours. And with OAT, the same program runs in roughly 2 hours. So this shows that the C flat and OAT approaches and also the other prior approaches, they impose a very high overhead on all the benchmarks, and the reason for this is the high number of T domain switches, which are being made to record the path measurements in the secure storage. Now, if you, this is not evident from these prior works. Actually, if you go and read their papers, then in the papers you'll find that CFLAT reported only 0.13% overhead for syringe pump benchmark, and OAT reported an average overhead of only 2.7% on 5 embedded programs. Now, what is the reason for this low overhead reports by these works? So the first reason is that they evaluated their approaches on small embedded programs, which had only few hundred of control flow events. So if there are only few hundred control flow events and you multiply it 190 microsecond overhead per switch, then that is only few milliseconds, and that overhead will not be visible. And then the second reason is that they attest only some critical sections of the program and not the entire program, and thereby they are able to report low overheads of the CFA mechanism. And it has been shown in the prior works that if you attest only some critical sections of the program, then there could be bugs in other parts of the program which can be exploited to still temper the execution of the program, and it will go undetected because you are not attesting the entire execution of the program. So we concluded from this study of the prior works that the prior works are extremely slow and they attest only some parts of the program. And so in our work, we want to develop a whole program control flow path attestation mechanism with near practical overheads. And so we have this work blast, which was published in ACN CCS 2023. So there are three key contributions of our work. The first one is to reduce the T domain switches by local logging, because we identified that that is the key reason for the high overheads. Second is that, as you just saw, that in C flat, the overheads were 1000x, and in OAT, it was only 500x. So they were able to reduce the overhead only by changing the locations where you are recording. So we adopt a more optimal path measurement instrumentation mechanism, which is Ball-Loris path profiling. And lastly, the attestation reports are usually they are like 100 megabytes of sizes, and so we also propose a more compact and expressive path representation using whole program paths, WPPs, which generate a context-free grammar of the attestation report, which is generated by Ball-Loris path profiling, and which is only like few kilobytes in size. So in this talk, I will be talking only about the first and second contributions, and the third contribution I can talk about if there is time and if you're interested. So the first part is to reduce the overhead is reducing the T domain switches by local logging. So in this, so on the right hand side, on the left hand side, which is the rich execution environment, as before we have this program control flow graph which we are attesting. And this is the process address space, which has the code and the data region. And in the data region, we are going to allocate a log region where we are going to record the path measurements. So the overhead is happening because every time we are making a transition from the normal world to the secure world, and we want to avoid that. To avoid that, we are creating a log in the data region or in the process address space. So now, instead of recording in the secure storage, we record in this log. So instead of one domain switch overhead, we have to only pay the cost of one memory write here, and so we only have to pay the cost of memory writes. And so here, so we are recording here, and as the program executes, we are going to record these basic block IDs in this log. And when the program finishes execution, we are going to switch to the TEE, and we are going to flush these log entries into the TEE, which is going to then sign these measurements and send it back to the verifier for verification. Now here we have reduced the number of T domain switches from 4.
Hello, Miss
Yeah.
Nikita. See, yeah, you will get a lot of advantage by this, but I think why they were storing in the secure storage is because they don't want that to be overwritten by some other malicious program.
Yes.
Now, you just brought it back to your address data space. So, wherein there is a high chance of whatever you are recording that getting modified.
Yeah, we have a protection mechanism for that, which I'm coming to in the next slide.
Okay.
Yeah. Yes, so here we have reduced the number of domain switches from 4 domain switches to only 1, and therefore we will be able to reduce the runtime overheads. But as it correctly pointed out, this is not secure because the code here can write to this log region as it is part of the same address space. And so what we do is that we will check all the store instructions. So there are these two kinds of store instructions in the program. One is which we add. So the instrumentations which we add can write to the log, but the store instructions which are already present in the code should not be able to write to this log region. So we are going to so if the store instruction write to the log, then it can corrupt the log and therefore corrupt the measurements that we are accumulating. And so to protect the log data, we are going to check this address, the store address. If this address is not within the log, then we allow this operation to happen. But if this address is falling inside the log, then we are going to abort the process because this is a malicious operation. And to implement this, we use software fault isolation, which is also well-known technique. Yes.
Yeah. Again, whenever you are writing like this, again, this will add some overhead, right? Whenever you are
Yes.
checking whether this is within your address range or not, again, this will add some overhead.
Yes. Yeah, it will add overhead, but it is much less than the overhead which we have to pay if we make a domain switch from the normal world to the secure world.
Okay. Okay.
Yeah. Yeah, we have in our experiments, I will come to the overheads by SFI in the experiments. Okay. So the store instruction here, we are going to put a check after the store, SFI check after the store instruction, which is going to take the store address, mask it, and then it is going to check whether this masked address is compare it against the log start address, and it will check whether it is equal or not. So if it is equal, then the address falls within the log region, and then it will abort the process because it is a malicious attempt to write inside the log region. So this overall, we have created a log region. We have modified the recording operations to record inside this log region, and then we protect the log region with the SFI mechanism. So this entirely, and only when the log becomes full, then we are going to flush it to the TE. So this overall mechanism we use to reduce the number of times that we have to switch to the TEE, and this helps us reduce the overhead. And now the second contribution is optimal path measurements. Um, Now we observed that the measurement approach used by C-flat and node, they are not optimal. And so Ball-Loras path profiling is a is a path profiling algorithm from the literature, which is provenly better than the bit tracing algorithm used by OAT. And therefore, we employ this to reduce the number of times that we have to record in this log. So here, whenever the log becomes full, then we have to switch to the secure storage and record and flush our measurements there. So the number of times the log becomes full is equal to the number of times we have to switch. So in order to reduce the switches, we want to reduce the number of log entries. Okay, so that's why we are using a more optimal instrumentation strategy here, which is the Ball-Loras path profiling algorithm from 1996. And this Ball-Loras path profiling algorithm selectively instruments some of the edges. So it adds a arithmetic operation on some of the CFG edges here. And this operation, this arithmetic operation basically increments or decrements some register value. And this register we are calling the ball-lowress register, which is set to value 0 in the entry basic block. And then it is modified. And ball-lowress algorithm ensures that if there are n acyclic paths in your procedure, then every acyclic paths get a unique integer path ID. So if there are n acyclic paths, then every path will get an ID in the range 0 to n minus 1. For this particular example, if this yellow path is taken, then R is set to 0, the register is set to 0 in the entry basic block. Then on this path, there is no ball-lowress instrumentation. So in the end, when this basic block 6 finishes, that is the return instruction, then you are going to store the value of R in the log. Here value 0 indicates that the rightmost path was taken. This path BB1, BB2, BB5, BB6 was taken. In contrast, if this leftmost path was taken, then R initially was 0. Then on the first CFG edge here, R plus equal 1, that is the register operation will, the register arithmetic operation will increment the value of R by 1, making it 1. And then when you exit from BB6, then you will write here 1, indicating that the leftmost path was executed. So here there are only 3 acyclic paths, and every acyclic path has a value, different value in the range 0 to 2. And ball-lowress path profiling algorithm also works for cyclic programs. Basically, it breaks the cyclic programs into acyclic, these acyclic parts. And for that, it at the loop headers, you are going to store the value of the ball-lowress path value in this here in this log, and then on the again when you are entering the loop, you are going to reset it to some appropriate value so that next time when you record, it will be a different value, indicating a different acyclic path. And same as for call instructions, whenever there is a call happening to other procedure, then the current value of the ball-lowress path register is recorded, and then it is set to 0 in that new function. And when you come back, then you again reset it to some other value. So at all times, you are maintaining that acyclic paths in your procedure have different IDs. And again, whenever you're going to write these path IDs in this log, and every integer path ID corresponds to a unique acyclic path. And whenever this log becomes full, then you're going to switch to the TEE and accumulate. So in contrast to C flat and OT, it records less number of times. And therefore we are able to record, we are able to reduce the size of the log here, and also the number of times that we have to switch to the TEE. Now, to evaluate the effectiveness of ball-lowress path profiling algorithm compared to the approaches used by C flat and OT for recording, we computed the log entries with the BLAST and other approaches. So compared to C flat, our approach records 7 times less log entries for Nettle SHA-256 benchmark. And for the prime count benchmark, it records approximately 3 times less log entries. Now, for some benchmarks like CRC32 here, BLAST records more log entries compared to OAT. And this is because in OAT, they did not record direct calls, but in BLAST, we record all types of call instructions, both direct and indirect. And therefore, we found this issue, and then we tried to handle this by using function inlining. So we inlined functions up to a call depth of 5, only small functions with less than 1000 LLVM IR instructions. And we were able to improve the performance of certain benchmarks, but we do not advocate to use it blindly, because in some benchmarks, it also deteriorates the performance if you use function inlining. And for our experimental setup, we use Raspberry Pi, and the program we have evaluated on MBench IoT benchmark. We take the benchmark, and then we compile it with LLVM IR pass. We have written a compiler pass, and this compiler pass adds instrumentation both for the BLAST both for the ball loaders path profiling to generate these path IDs, also the software fault isolation to protect the log region, and also to make these T domain switches whenever the log becomes full. And then we give this pass to, we run this pass on Raspberry Pi, and Raspberry Pi 3, which we've used, has a ARM trust zone that we are using by leveraging Opti framework. So to compare the performance of our approach BLAST with the prior work C flat and OAT, we compared the overhead runtime overheads. So the y-axis represents the runtime overhead in percentage, and the x-axis are the benchmarks from Image IoT suite. And here the black bars are for C flat, the orange bars are for OAT, and the green bars are for BLAST. But if the first thing I think you will notice is that there are no green bars here, which clearly shows that the BLAST overhead is very low compared to C flat and OAT. And now to zoom in on BLAST overheads, we compare it with the baseline. And on the y-axis, we have the execution time of the programs with on the row binary, as well as when it is compiled with BLAST LLVM pass. And then the black bars here represent the baseline. The green bars are the BLAST binaries. And this pink bar here is the average runtime overhead that we have achieved with BLAST, which is the best of when we use function inlining and not function inlining. So this is the runtime overhead, which is 67% over the baseline. Now coming to the runtime overhead breakdown. So there are three factors which contribute to the runtime overhead. The first one is the SFI instrumentation. Second one is the ball loaders instrumentation, which are majorly only the register arithmetic operations. And the third one is the log hashing. Whenever the log becomes full, then we are going to switch to the TEE and record the path measurements there. Now here we assume the presence of multiple cores. So we are using one core for switching to the TEE and recording it, while parallelly the program is still executing and recording the measurements. So that is why the log hashing operation majorly happens in parallel to the program execution and contributes negligibly to the overheads here. And only in some programs where the log is filled faster, it shows as the wait time. And then as you can see that the bulk of the overhead is due to the ball loaders instrumentation, which are the register operations, and SFI instrumentation roughly on average contributes to 25% of the overheads. Now, we also compared our approach on the syringe pump benchmark, which was evaluated by C flat, and we ran it for different amounts of bolus, which is the amount of medicine we want to inject, which is from 0.5 to 2 ml. So the baseline execution time of this program is 1.28 seconds for 0.5 ml bolus. With BLAST, it takes 1.42 seconds compared to 1.28 seconds. And for 2 ml bolus, the baseline execution time is 5.12 seconds, and with BLAST, it takes 5.28 seconds. And in terms of percentage, it is 10% for 0.5 ml and reduced to 5% and 3% for 1 and 2 mLs. While in the case of C flat, the row overheads reported in C flat paper for 0.5 ml are 1.2 seconds, then 2.4 seconds for 1 ml and 4.8 seconds for 2.4 seconds for 1 ml and 4.8 seconds for 2 ml, which is approximately 93% overheads. Now, I would like to conclude this part of our the BLAST work. So in the BLAST work, we have used software fault isolation and ball loaders instrumentation together with the idea of this local logging to bring down the number of times that we have to make the T domain switches. And it helps us reduce the performance overhead to only 67% and we have done our experiments on Image IoT benchmarks. And the overheads that we have are significantly lower than the prior works. Sorry. Yeah, so for the future directions, so there are different work, there are different things that we can still work on this area. The first one, of course, is the more robust and practical implementations. So current work, so the current work that I've shown, it doesn't support any libraries or multi-threaded programs. So if your program is compiled with some libraries, then the libraries are not attested. And if your program is multi-threaded, that also is not supported. And then we can also further optimize CFA instrumentation and implementations, because what we have done here is not completely optimized. It is only a research prototype, and it is there is still scope for more optimization and bringing down the overhead further down. Then the second part is secure CFA in the presence of untrusted normal world OS. So as I said in the beginning, that we assume that the program is running on a bare metal setting. So in other settings where the operating system is present, then the current CFA approach is not secure, because our threat model is different. The assumptions are also different. For example, one of the assumption is data execution prevention. So since the OS is a privileged software, it can disable data execution prevention, and therefore the CFA mechanism is no longer secure. And therefore there are different new kinds of attacks, and then therefore we need new defenses to protect the CFA mechanism in the presence of this untrusted normal world OS, which we are working on currently. So this is work in progress. And then third is CFA for heterogeneous cyber physical systems. So sometimes it happens that there are multiple components of one system, and some of the subsystems may not have a secure hardware, but it might be present on other hardware. For example, in case of a drone, there are two boards. One is the companion board, other is the flight control board. And the companion board, the flight control board is the navigation, handles the navigation part, but it does not have a secure hardware, but it does a lot of critical operations of this of the drone, like the navigation. And in order to attest that part of the operation, we want to have a secure hardware, but it is not directly present there. So how can we leverage a secure hardware which is present on the other component? It presents new challenges and that are yet to be solved. And lastly, with attestation, we are able to detect these kind of attacks. We are able to basically detect that there is an attack, but there is very less work present which uses these attestation reports to find exactly what bug was there, and do a study of this attestation report to detect exactly the cause of the attack, and then use that to uh, resolve the attack situation. So with that, I would like to end my talk. Thank you so much for listening. I'll be happy to take question. This is my email ID and my advisor's email ID, and we will be happy to connect with you offline as well. Thank you again.
Hello.
Yes.
Yeah, so can you go to slide number 25?
Yes.
25.
Yeah.
Yeah, so like here you are checking that whether the writes done in the log area is from a valid code or not. So
Yeah.
is there any chance ki matlab you have written this verifier? I mean, you might have written some code to check this, right? So what if like that code itself is manipulated? I mean, is there any chance?
Yeah, so for that, we are relying on data execution prevention. So we are saying that if this code that we are going to run, first of all, when it is loaded, we ensure that this is the binary that we want to run. So we compute the hash of this binary, and then we verify it that this is the binary that has these instrumentations that we want to run. And then once this binary is loaded and it is executing, then there is data execution prevention in place, which ensures that the attacker cannot modify the code pages. They are only executable and not writable. And the attacker can also not add any code in the data region. Thank you.
Yeah, Devashish this side. So I have one suggestion and one question. So can you go on that slide where you were showing a graph where you mentioned that you cannot even show the blast performance or the blast results? I think it was
Yeah.
31.
Yeah.
Yeah, I think here you can use a log scale on y-axis because even if it is going to be minimal, it would not be zero. So then we can basically gauge that what is the overhead of blast even in this graph, because otherwise it looks like that, maybe it could be nearly zero or something, but it would not. 67% is a huge number when we compare it to the baseline, correct? So log scale will actually show that, and I think it would be a fair comparison with the others. So that is one suggestion. And I have one simple question, maybe I missed that. So in my understanding, if there are, let's assume, n inputs corresponding to n inputs, maximum possible, there could be n paths in the CFG, n valid paths in the CFG that you can attest. So how you ensure that you have basically all the possible n valid inputs? How you check that? Because it is dependent on the input, am I right? Depending on the input there will be a path. So, and I can create like infinite combination of inputs for any binary. So how you ensure that the input space you have like completely tested?
Okay, so your question is regarding to the measurement database, that how we create that for these inputs, which can be say n inputs, and then of course there can be more inputs, right?
Yeah, it's not only about the measurement. Like, let's assume I want to use your approach, correct? And I use this blast. So maybe blast says that there are, say, 50, or maybe, for example, for the discussion's sake, 100 possible valid paths, correct? But now I come up with a corner case scenario, say a new input which is a valid input, but maybe you missed it or the blast missed it. So how you basically ensure that I am not missing the valid input?
Yeah, so we have not like implemented it for some particular range of inputs. It's the program has been instrumented to record whatever it is doing. So if you can give it any input and it will record. So it is not only for these n inputs that we have predefined for which it is going to
Okay.
record. So it has been instrumented and it will record irrespective of what input is given. And when you have this recorded trace, then you have to verify it. Now, for the verification part, you need a mapping corresponding to the input that you have given, which you
Mhm.
can create in a benign setting. Does that answer your
Uh,
question?
Maybe I can take it offline, but yeah, the answer that you give does not answer my question, because in my understanding, in even in the benign scenario, you have to give some inputs, and corresponding to that, there will be
Yeah.
some paths that are going to be created. But there can be
Yes.
like
So
n
then
number of
then
inputs, correct?
right.
No,
So then the
okay.
question, yeah, I
Yeah,
would
I
just
think
like to.
what I understood from him, his question is that if that path with respect to that input is missing in that measurement database,
Yes.
post tracing or post recording, someone can understand, okay, we might have missed it, and they can include it. That is anyway a kind of database only. And she is not doing any work to prevent. Her job is only to record, and it is for audit purposes, right? And if
Yes,
it,
that is
I
right.
don't think she is working towards, like, if the path is already there, and if that path can be checked while the program is getting executed,
I
and for
see.
that input, if that is deviating from the input path because it is already predetermined, then
Mhm.
that execution itself can be stopped. But that's
Mhm.
not what she is doing, I think. Am I right?
Yes.
Yeah. So it is post. It is, I mean, her job is only to record, and then later it will be verified by the verifier. So if the verification also has to happen while the execution keeps happening, and if the path is, whatever path is getting executed, if it is deviating, and it can be stopped then and there itself. And I don't think I that is the objective of her research. Am I right? It is post audit. It is auditing purpose,
Yes.
not
Yeah.
prevention purpose.
Yes, the purpose is auditing. So you record what is happening and then you verify it later after it has been done.
Okay, thank you.
But definitely it's very good work. Real, quite interesting. Thank
Thank
you
you so
very
much.
much.
Thank you.
Thank you.
Hello.
Yes.
Hi Nikita. So I'm Nishkash, first year MS student from IT Bombay. Thank you for your talk. I had I guess 2 to 3 questions regarding your work. Firstly, you talked about writing to a specific location in the memory, logging into a specific location in memory whenever the basic blocks are getting executed, and you had a system in check in place wherein you are not allowing any normal store to write to that. So, is there any specific condition of check for a read which a program can do to that particular block?
No, we are actually not considering privacy, confidentiality. So the program can read it, but it cannot write.
Okay, so just by reading it, no information could be deduced of what logging has been done, and is it?
The attacker can read what is being recorded, but it should not be able to modify what is recorded there, because we want it's a proof of integrity. We are generating a proof of integrity of execution. So we are recording exactly what the program is doing. But what the program is doing, if the attacker comes to even know, that is okay.
Okay, I see. And you showed a table in the starting of the presentation wherein you classify different branches and how C flat, OAT, and your work considers those branches in your profiling. And then you talked about a method wherein you have values in registers being incremented, which actually tracks that. If I'm correct, is that the method wherein you're considering which branch to choose?
Could you repeat your question?
Okay, so there are different kinds of branches. You showed a
Yes.
table mentioning different kinds of branches, and in your method, specific kinds of branches are chosen, and some are not chosen. Yeah, this one.
Yeah.
Yeah, so which one is chosen and which one is not chosen? How do you make a decision of uh, profiling them?
Okay. So we're using Ball-Lawrence path profiling algorithm. In that, we do not need to break the program path, like acyclic paths, at conditional branches, except the loop headers, because the loops create cycles. So we break it at loop headers. We are going to record what is the current path value, and then we're going to reset it. And apart from that, we do not only those loop header conditional branches have added an instrumentation, but apart from that, all other conditional branches like if else or unconditional jumps, they are not, we have not added any instrumentation there. While in case of OAT, they've added it on all conditional branches like if else, switch cases, or loop headers, all of them. And then we have it instrumentation also on all the call instruction, because in the call instruction you are moving to the other procedure, so you have to record the path and reset value for the new procedure which is to be executed. Does that answer your question?
Yeah. Uh, yeah, and just out of curiosity, was there any specific reason you chose embedded binaries to work on and not real system to work on? Because there are multiple attacks which come up on real systems, and attestation would help mitigating them.
Yeah, I think it is because the prior works, they have also done work only on embedded systems so far. And so that is the reason, that is why we have also done it for embedded systems. And also this assumption that we have, that is bare metal, the application is running directly on bare metal, which is not true for these general other desktop systems or other places. But we are currently building a more like a more sophisticated or a approach, building a CFA approach, which is also secure even in the presence of an untrusted OS, so that we can then do these like apply attestation also in other domains, which are more complex.
Okay, yeah. Those were my questions. Thank you.
Thank you.